First lesson on exponential models. We're going to be looking at graphs initially of exponential functions and logarithms. And to do that, the best thing you can do is use Desmos or GeoGebra. They both have apps for your phones. The internet browser versions are brilliant. Play around with it and it will help you so much. So that's exactly what we're going to do. Here's which one do we want? This one, Desmos. First of all, this is a graph of, well, in this case, y equals 2 to the power x. So here, over here, I've got y equals a to the x, and I've got this slider. So if you type in y equals a to the x, it says add slider. You click on the button, add slider, and it gives you this ability. And what we can do is see what happens. A currently is 2. That's what it looks like. So we can see here 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, just off the graph. So what happens if I increase 2? Well, if I'm doing 2 to the power, I do 3 to the power, then I'd get 3 to the power 1 is 3, 3 squared is 9 all the way up here. So we can expect this graph to be steeper up this way. What about if it's 3 to the minus 1? Well, 2 to the minus 1 is a half. 3 to the minus 1, 1 over 3, will be a third. It will be smaller. 2 to the minus 2, this graph, will be 1 over 2 squared, using our index laws. A quarter, which is about there, which is there. 3 to the power of minus 2, that will be 1 over 3 squared, will be 1 over 9. So that will be much smaller. So we're getting smaller down here, but bigger up here. And we can see that. Let's move the slider along. And we can see that's exactly what's happening on the right-hand side. It's getting steeper. On the left-hand side, it's getting closer to the x-axis. And as we drag that down, we can see what the opposite happens. As we get smaller, it gets less steep. And over on the right-hand side and further away. So here, a to the power of 1.3 to the, y equals a to the power of y equals 1.3 to the power x. We've got less steep over here and further away from the x-axis over here. But what happens if we bring this to be 1? Well, at 1, there we go. At 1, we just have 1 to the power 1, 1 to the power 2, 1 to the power 3. Everything is the same. And then as we make this negative, we get basically the opposite of what we've had before. Let me just, not negative, I mean less than 1. There it is. So here we've now got a is 0.5. So we've got 0.5 to the power x. So here, 0.5 to the power 1 is 1, 0.5, a half squared is a quarter, a half cubed is an eighth. And over here, we're going to get a half, and then to the power minus 1, that's 1 over a half, 1 divided by a half, or just 2. Here, we're going to have, so that's, yeah, reciprocal of a half. And so on, basically, you get the opposite happening. And if we continue this further, as we get closer and closer to 0, it gets closer and closer to that until it just disappears. In fact, 0, you get this, sorry for wobbling around all over the place. Come on, computer, you're told, there we go. 0, you get just those values. 0 to the power 1, 0 to the power 2, and so on. That all makes sense. It's all just 0. 0 to the power 0, mathematicians argue over. Some people say it's undefined. Some people say it's 1. But negative 0 to the power of negative numbers, they're just undefined for now. So that's what that looks like. Okay, we can then play around with logarithms. So let's get rid of this thing. Okay, and logarithms. Oh dear. Okay, so as we discussed before, logarithms are this inverse function of exponentials. So what we get is a reflection in the line y equals x here, and this is then the logarithm base 2 of x. And again, we can play around with these numbers. What happens if I change the base? So currently base is 2, and if I increase the base, you can see the main thing I want you to understand here is that the graph doesn't really change that much. It kind of flexes and changes a little bit. Let's get rid of that, we don't need that anymore. But ultimately, the shape of it is much the same. So it doesn't matter what base you have. Notice it always goes through the point 1 in the same way, actually, that y equals a to the x also always goes through the point 0, 1. And so the graph is really much the same whatever happens. The other thing that we can do is add and subtract things within the bracket. So currently this is just log to the base 2 of x. Let's change d. So d is currently 1, so we've just got 1x. Let's make it 2x or more. And can you see how, as I increase that, the graph is just sort of moving upwards. In fact, it's doing two different things. One way of describing it is it's being translated vertically upwards. We'll look into why in a moment. The other way you can think about it is it's actually being stretched by a fractional scale factor. As you increase d, it's being stretched in this direction here. And we know about that from transformations of functions. So it's well worth doing a little bit of a recap there if you've forgotten that. Okay, let's put that back to 1. So we've just got 1x. And then the other thing that we can do is add or subtract something here. And again, as we would expect, that just translates the graph left and right, depending on whether we're adding or subtracting. Here, if I'm subtracting something, it moves it to the right, adding something, it moves it to the left. So that gives you a rough idea of what these things look like. Let's make some notes. So here, key things to note are that if we've got y equals a to the x and a is greater than 1, then we're going to get a curve that looks like this. This is y equals 2 to the x, and this is y equals 4 to the x. So the bigger that value of a, the steeper it is here, the closer it is to the x-axis, but it still goes through this point 0, 1. This is essentially an asymptote. It never crosses that line. It will get closer and closer to it, but will never cross it. So the whole of the exponential function is above the x-axis, is positive. None of it is ever negative, nor either is it equal to 0, although it gets close to 0. The other thing to bear in mind is we could rewrite y equals 4 to the x as y equals 2 squared to the power x, or 2 to the power 2x. So if we were to put, say, a constant there, k, as we increase k, that's a bit like increasing a. It has the same effect because we can treat that as a to the k to the power x. So instead of increasing a, I could just increase k, and that would have the same effect as changing 2 to 4. It's going to make it steeper on this bit and closer to the x-axis there. If a is equal to 1, then we've just got 1 to the power something, which is always 1, so we get this green straight line. And if a is less than 1 but bigger than 0, then instead of increasing, we're going to get something that decreases. And in this case, this is y equals a half to the power x, 0.5, which is a reflection in the y-axis of y equals 2 to the x. We're going to talk a bit more about exponential growth and exponential decay next lesson, but suffice to say now, this is what the exponential growth looks like. Something that is always increasing, always getting steeper and steeper and steeper. And then exponential decay, for example, with radioactive materials, that would look something like this. It never gets to 0, but it's always getting, it's always reducing. It reduces very quickly to start with, and it reduces slower and slower and slower. Logarithms, the key points always goes through 1. The x-axis is an asymptote. It's always above the x-axis. They're your key points. Your log graph is a reflection in the line y equals x of the exponential curve to give you this log curve. And it doesn't matter what a is, the base here, it's always going to look something like this. In this case, it's y equals log to the base 2 of x. Notice if the exponential graph goes through 0, 1, then the log graph is going to have to go through 1, 0. And this time the y-axis is the asymptote that we're interested in. Some of the questions that they might ask you are to do with sketching these things, and there's two things that we need to note. Firstly, how can you use graph sketching to determine the number of solutions? In this case, we want to rearrange this so that we've got two equations, one on each side of the equal sign, that we know how to plot. So if we rewrite this as log to the base 10 of 10x equals 1 over x. So now we can plot this. Certainly the 1 over x we should be familiar with. Looks something a little bit like this. Okay, and the 10x, log 10x, we can say, let's just change the color. So this is going to be a green graph over here. We can guess it's going to look something like this because the log graph didn't really change that much. But we're going to need to use transformations of functions to know exactly where it passes through here. So we've kind of already answered the question. It's only going to have a single solution, one solution. To be a bit more specific about where this graph crosses the x-axis, we want to think about transformations of functions. Here we're replacing x with 10x. So that represents a stretch, scale factor a tenth, parallel to the x-axis. So instead of crossing at 1, it's now going to cross at 1/10. It's all been swashed in that direction, closer to the y-axis. Okay. However, and this is a hint for this question here, we could rewrite this. Log 10x equals log to the base 10 of 10 plus log to the base 10 of x. Log to the base 10 of 10, well, what power do you raise 10 to get 10? Well, it's just 1. So this is 1. Okay, which is the same as taking the log of x and then translating it up 1 to look something like that. So there's two ways of describing the transformation that takes log x to log 10 of x. And the second way comes from using the laws of logarithms. That should be now enough information to have a go at exercise 8a, just question 1. We're going to do the rest of the questions in the next lesson, and 8b, all of the questions. Remember to read the textbook. The examples can be really useful, and take your time. No problem.